Good afternoon, ladies and gentlemen. So I'm very pleased to be here to talk about something about the large deformation of railway tunnels in Slate-Schistose rock in China. I'll talk in the following three parts. Firstly, some background information about railway construction in China in the recent years. So, railway construction in China developed very quickly, very rapidly these years. We have a plan in 2008. We plan that we will have 41,000 kilometers railway to be operated in the next 30 years. In last year, we have 38 lines of railway under construction and 100 billion of RMB input to the construction. Okay. Thank you. And this year, we largely increased the investment for the railway construction. The annual investment will be 800 billion RMB since this year. But the 80% of the railway will be Western China. In the construction for railway, the tunneling is a big part, but it is a very difficult part, especially in mountain area. We plan that we will have in the future 30 years 10,000 railway tunnels with a total length of 10,000 kilometers. So I just list some tunnels here, railway lines here. Why don't it work? Okay. So this is some railway lines started from 2008, 2009, and 2011, at least recent years. The two lengths, both of them are over 500 kilometers with a very high speed. But a great percent of the railway are tunnels, 70%. What we may encounter in the construction of tunneling: water problem and caving and rock burst and high temperature, but most difficult problem is large deformation. Under the high stress, deep excavation and soft rock. So there's some tunnels. The cases of tunnels. The name of the tunnel and location of different lines of railway. This is a total. What's the problem? Oh, this is the length of most of our very long tunnels. Some of them over 20 kilometers long. But rock are very soft. Milanite, carbonaceous slate, and some very finite, some very soft rock. So this is why the tunneling is very difficult. Why? What's the causes for the tunnel large deformation? Two main causes. One is the high stress or deep excavation. Two different reasons cause the same problem: high geologic stress. We have some typical ridges, the mountain area, and we have also some compressive zone in China. This is Tianshan, and this is Qinlin, and this from Nongmenshan and to the south of China. And as other aspects, the rock are very soft. For the yellow color, blue color, all of them are sedimentary rock or para-rock. So the soft rock is widely distributed in China, especially in Western China. So this is some basic information, background information. Here I am going to put some cases in Nanyu Railway. Nanyu Railway is from Nanzhou in northwest China to Chongqing. This is Guangyuan, and then this is Chongqing. The total length of the line is 820 kilometers. But most tunnels distribute in this part because the railway goes across Qinlin Mountain. We have 66 tunnels, which takes more than 300 kilometers long, takes 17% of the total length of the line. So all these tunnels, most of these tunnels have not finished till now, even though they start to construct from 2008. There's some information for the tunnels. The name and the names, you can see that most of them are non-tunnels. Depths, most of them are over 200 meters. Not over 500, even more than 1,000 meters deep. But another aspect, I just mentioned that the rock are so soft. So we can see some pictures that this is a structure of the rock. Carbonaceous slate and phyllite, very thin slides. And for the geologic stress, it's very high. We have measured in 10 points along this line in about 400 kilometers long. All of them are over 10 megapascal. Some very high ones, over 30 megapascal. So these two factors combined each other to lead to a very difficult problem, large deformation. So some tunnels, most of the tunnels deformed into 300 to 500 millimeters, and part of them reached 1,000 millimeters. So this is a very large converging deformation. And this led to most of the tunnels have to change their quality class from very high class to lower class. This means we have to put more money for the leaning system, for the supporting system. You can see around 62% of tunnels have upgraded their leaning system. Someone reached 95%. Here are some cases. Case one is Muzhailin tunnel, not very large deformation in different sections. This 500 for the converging deformation. And these are some different sections. Case 2, Xinchengzi tunnel. Its length is about 9 kilometers long. The maximum of depth 450 meters. Very weak rock. The the balance of the rock just parallel to the axis of the tunnel with a very deep angle, very big deep angle. So this map of the tunnels, 2 single tunnels goes gradually to emerge to a big one, include the underground station. So with the going of the tunnels, the interwall became thin and thin, very narrow. So the stress concentration very strong. So they make the excavation and construction more difficult. The most difficult part is this part. So in the construction, we can find a serious, terrible phenomena. So the ground uplift and breaked. The first leading system breaked. Even the second, the terminal system, the supporting system are breaked. So we have to replace the first leading and then make new ones. This is the design for the new system, strengthened leading system with several layers of different leading. Case 3, Liangshui Tunnel. You can find the depth is not big, 220, but it's under the slope. So, and symmetric stress act on the tunnel. This makes the tunnel very special deformation modes. In this corner, deformation inside to the tunnels with this amount. But in this part, it go out. So, also the support system is seriously broken. This is top. And this is second leading system, and this first one. So we also need to replace the leading system already constructed, and then use a new one, take a new one with a very thick steel concrete support system. So, from the construction of the tunnel in the mountain area, what have we learned from the process? Firstly, what's the reason? What led to the large-term deformation? I think 2 reasons I just mentioned. One is because the rock is very soft, but originally, it's not so soft. When we excavate it, it will deform, and this deformation will make the rock much more soft, much more weak. This is the first reason. Another one is the strengthening of the rock pressure. Why it will strengthen? So I'll explain it. So this is for the first reason, the soften. We call it structural soften of the rock due to excavation. Originally, when we did not excavate it, the rock just like this, a serious hard sheet connected with the schistose minerals connect each other. So this block just like a hard block, like a brick. It's very hard. So we can classify this rock into class 3, a very high quality rock. But when you excavate it, the rock deformed, and with some action of water, the connection between the hard sheet, hard slice break. They lost the connection, lost the cohesion between the slices. After the exhibition and the deformation, the block changed to a stack of paper, very thin paper, very easy to deform, very flexible. So this is the process for the softening of the rock. You can see that this is rock. What is the strength of the rock pressure? By the experience and our technical standard, at least in China, I don't know what's in the other country. The designed rock pressure generally less than 0.5 megapascal. But why the linear system breaks so seriously? It must be the big rock pressure. So we make some measurements. We measure a series of sections of tunnels. This is Liangshui Tunnel, Zifang Tunnel, Tianshan Tunnel, Jinchen Tunnel, and others, many tunnels. We make a series of measurements for the rock pressure. You can see that this 1.2, and this 1.9, 2.6, and then what, 2.1? Much bigger than the experience. I think this is another reason for the natural deformation and the breaking of this supporting system. The second, what I learned from the experience, how we decide the linear system in the current mode. So in the current mode, firstly, we classify the rock by investigation, considering the strength of block and the structure of the rock mass. Then we classify the rock, and then consider the influence of geostress and the groundwater. We modify the class. So based on this modified class of rock, we have some standard linear system. At least in China, we dig like so, like this mode. But what's the problem? Who can help me, please? So I just mentioned, because of this reason, so many tunnels bricked, and the rock quality class have to be decreased. So this some data for the proportion for the with modified the rock classes. Averagely 72%. So why the rock quality changed from they have the yellow river, yellow color. Some of the tunnels, for some of the tunnels, we have to change the quality class of rock from class 3 to class 5. This is a very big change for the design of the tunnel. How to explain this phenomena? How can we change the class of the rock of quality from 3 to 5? So we did some research work on this. Firstly, originally, we decided rock quality as 3 class by classification and investigation in the investigation stage. And then we excavated and the rock mass deformed, lost the interlayers segments. So we can calculate by the static mechanics of rock mass, which is proposed by myself, just reintroduced by the chairperson. We can calculate the parameter, the deformation parameter, by these theories. The elastic modular can be reduced to 3.5% as the original state. And then we make a map in this. So we can find this is very, very strong and isotropic. The minima over the return, the minima and the maxima reach this is 3%. Very big difference in different direction. Not only the value muchly reduced, but different, very, very big difference in the different direction. And then we can transfer from the deformation parameter to the class of rock, classified rock class by this experience formula. So we can confirm that just because the excavation and deformation of the rock, the rock class, rock quality will be very sharply reduced. So then what should we do? Firstly, we should modify the rock classification system, especially for this kind of schistose rocks, the thin, very thin layers rock. We should have a very special class of this kind of rock with a very special design of the supporting system. And we need to change the routine of the design. The current routine is that rock quality classification and standard design. I think we need to change the model to the following one. Rock parameter firstly, and then design by calculation. So firstly, investigation and test, we get some parameter of the rock mass, and some modify, we get the parameter for the design, and the design by the calculation to the fated leading system. And at the same time, we can also transfer the parameter to the rock class grades, the cognitive grades, and check the design. We should also consider the unsymmetric linear system because the isotropic property of the rock will lead to the unsymmetric deformation. So we need unsymmetric supporting system. For the boat we need to goes across the sheet, different place with different kind of boating system. So as a conclusion, I have to for 5 points. The firstly, large deformation leads to loss of tunneling upgrades. The evaluated class of rock replace their delayed time and increase the investment. Certainly, the main causes of the problem are strengthening of rock pressure and softening of slate of rock due to excavation, deformation, and other reasons. But the current rock classification could not reflect this change. The third, the current routine for leading design based on the rock classification seems to be more precisely reflect the feature of the rock mass. For example, influence of excavation and isotopy of the rock, etc. The fourth, a parameter-based design method seems to be more reliable than the classification-based design. Fifth, the asymmetrical support system need to be taken into account for tunnel in anisotropic slate-schistose rock. That's all. Thank you.